Hi everyone. In today's lecture, we will discuss about frequency response of first order systems. So, in the previous lectures, we discussed about impulse response, step response, and we also discussed about Laplace transforms, and we introduced a term called transfer function HFS, and we said that understanding the transfer function is sufficient to understanding a system. We also spoke a little bit about poles and zeros, and we said that with the knowledge of the poles and zeros, you can say if the system is stable or not. And we also said if the system, we also said that we can predict the outputs of the system for certain given inputs. So in this lecture, we will now start analyzing a system by feeding sinusoidal inputs to it. So say we feed an input cos omega t. It's a sinusoid which I am going to feed as an input to this system. Now, we know from basics of signals and system that any LTI system, if I feed a sinusoid of certain frequency omega, the output frequency will also be same. Okay, but what will change, because that comes from linearity, what will change then is the amplitude and the phase. Now what I will do here is I will vary all the frequencies from vary the frequencies from 0 till infinity, and then for each frequency I will record the amplitude and the phase. Okay, so essentially I am going to record the amplitude and the phase for each frequency. Now if you see, the input frequency and output frequency are the same. The only difference is the amplitude and phase. So I will form a complex number taking the amplitude and phase. Okay. Now this function, this complex number contains information about the system's response to different frequencies. Okay. So that I am going to call it as h of omega, which is the frequency response. Now it turns out from Laplace transforms we introduced a term called transfer function, and when you evaluate S at j omega on the j omega axis, you get the frequency response. Okay. Now why do we go for frequency response is that what are we essentially doing in frequency response is that we are trying to understand the behavior of a system when you feed in a sinusoidal input. Okay, and we also know that any signal can be represented as a linear combination of sinusoidal signals. Most signals can be represented as a linear combination of sinusoidal signals. Now if I understand the behavior for sinusoidal signals, then it is equivalent to understanding the behavior for any signal. Okay, that's the main motivation for going for sinusoidal analysis. Okay, so now I have just said this, that frequency response, if you evaluate transfer function at s equal to j omega, that turns out to be the frequency response of the system. Okay, so I mean it should make sense, because instead of feeding in all frequencies, and varying the frequency of a sinusoid, I can simply feed a delta of t as an input to the system, right? Now delta of t, the Fourier transform is 1. So here I already assume that you know what Fourier transform is. You have taken a basic course on signals and systems. Okay. The Fourier transform of delta of t is 1. What does Fourier transform tell you? It tells you the distribution of energy contained in the signal across different frequencies. Now for an impulse that is 1, it means that the signal has, the Fourier transform of an impulse is 1. The signal has equal energies at all frequencies. Okay, so that is equivalent to feeding in a sinusoid with, a sinusoid with varying frequency, which it's equivalent to feeding all sinusoids of varying frequencies from 0 to infinity. So the response to an impulse will be if you take the Fourier transform of the response to an impulse, you will get your frequency response. Even that's a different way of defining it. But intuitively from basic circuits, if you want to understand it, it's just feeding sinusoids and looking at the output. Okay, that's what we are doing. Now, we will try to, our goal in this lecture is to plot frequency response for first order systems. We will take different circuits, and be able to plot frequency responses for it. Okay, so now I'm going to use this result. I'm not going much deeper into Fourier transforms and the theory of frequency responses here, because our purpose is more about circuit analysis than signal analysis. So you will find any standard textbooks on Fourier transforms, you can refer to that. Yeah. So first I'll take the simplest first order transfer function, which is 1 plus s by omega p, the single pole transfer function. Now I'll substitute s equal to j omega, I get the frequency response. Okay. Now h of omega, as we expected rightly, it's a complex number. Okay, it's a complex number, which means it has both magnitude and phase. So now we'll try to plot the magnitude and phase for this. When you take the magnitude, it will be 1 plus omega by omega p the whole square, and the phase variable, which is given by minus tan inverse of omega by omega p. Now first I'll try to plot this function, which is mod of h of omega, the magnitude response. I'll first start with two conditions. When omega is 0, the value of the function is 1. When omega equals infinity, the value is 0. Okay, when you substitute omega equal to infinity, you get 0. Now at omega equal to omega p, the value of the function becomes 1 by root 2. Okay, so the value of this function becomes 1 by root 2. Now if I plot this, I'd get a graph like this. Okay, now this is at omega equal to omega p. I am plotting it as a function of omega, mod of h of omega. Now I am going to plot the phase function, phase variable, same way across for all frequencies. When I say frequency here, it's omega is in radians per second. Now your phi starts from 0 degrees, and at omega equal to omega p, the value is pi by 4. It's an inverse tangent function. It is minus pi by 4, and then eventually it goes to pi by 2. Now what it means here is that if I feed a sinusoid of frequency omega p, for example, let's say I feed a sinusoid of frequency with amplitude 1, I am going to feed a sinusoid of frequency cos of omega pt as an input to the system. The output of the system is going to be cos of omega pt minus pi by 4, okay, with an amplitude of 1 by root. So you got it. I mean, I'm just writing the amplitude of the sine wave here and phase of the sine wave. What you will get essentially is 1 by root 2 into cos of omega pt minus pi by 4. And I could say this purely by looking at the frequency response graph. So I know for each frequency what is the response, what is the magnitude, and what is the phase shift. From that I can predict the output of the system given the input sinusoid. Okay, so that's the advantage. Now if you look at this function h of omega, the gain for higher frequencies is 0 and the gain for lower frequencies is 1. Such a function is called as a, or such a frequency response characteristic is called as a low pass characteristic. Okay, now I am going to use another term called filter. So here what it, you can also say that this signal permits lower frequencies and rejects higher frequencies. So it's like a filter which is filtering out higher frequency and retaining only the lower frequencies. So it's also called as a first order low pass filter. Okay, it's a low pass characteristic frequency response at first order low pass filter. Now here I'll come to a very important idea in circuits, which is actually how to plot the frequency response more efficiently. It's called the Bode plots. So what you do here is that we'll just take the magnitude response and make an observation. The magnitude response actually starts from 1, it goes to 1 by root 2, and then eventually goes to 1 by root 2 at omega equal to omega p, and then eventually it goes to 0 when omega tends to infinity. Okay, this is your magnitude response. Now when you look at this response here, I'll take two different frequency points. I'll take three different frequency points. Okay, I'll first take a point which is 10 omega p, 100 omega p, and 1000 omega p. Now if you look at the transfer function, the frequency response, the magnitude of the frequency response, you get a function like this. Now if I start from 10 omega p, for omega much greater than omega p, this function, I can ignore, this function is much greater than 1. So this reduces to omega p upon omega. So at omega equal to 10 omega p, the gain, the magnitude of the gain is simply 0.1 at 10 omega p. Now at 100 omega p, it's 0.01, and at 1000 omega p, it is 0.001. Okay. Now in engineering, when we are dealing with signals, okay, what is important to us is how much does a signal get amplified or multiplied by, or how much does a signal get, attenuated by. Okay, that's a very important quantity to understand. Now for example, if I look at this 10 omega p, the signal is actually getting attenuated by 1 by 10. Now if I look at this at 100 omega p, the signal is getting attenuated by 1 by 100 times. And I look at 1000 omega p, it's getting attenuated by 1 by 1000 times. But when I show all these things on a linear scale, okay, I don't capture the significance of what's actually happening in the system. So meaning, what I mean by that is, if let's say I ask you, compared to the frequency at 10 omega p, okay, what can you say about the gain at 100 omega p? Now I'll say that the gain at 10 omega p is 10 times larger than the gain at 100 omega p. Similarly, the gain at 1000 omega p is 10 times smaller than the gain at 100 omega p. But on a linear scale, if you see, I just take the difference between 0.1 to 0.01, it's very close to 0.1, 0.09, it's close to 0.1. And the difference between these two is 0.01 to 0.001, is again close to 0.01. Okay. Now on a linear scale, it doesn't tell me anything, but actually what's happening is that the gains between these two, the difference, the variation in the gain between these 2 points is same as the variation between gains between these two frequencies. Okay, that is not captured in a linear scale. So that is why what we do is we actually go to logarithmic scales. So I'll illustrate a very interesting property of a logarithmic scale. So when do we go for logarithms? Okay, so here log x to base 10. I'll try to plot this function and see when do we go for logarithms. Now logarithms are a very important mathematical operations which are used extensively in engineering, especially in circuit engineering. We use it extensively. The reason being that the gain or attenuation of a system, of any circuit, most of the circuits, varies by a huge number. It can vary from 10 power minus 12 to 10 power 6 or 10 power 12. I'm just giving out some numbers for amplifier gains and attenuating factors that happens in some systems. Okay, attenuation in filters, these are some very good attenuation numbers. Okay, so 10 power 8, these are the maximum gains you can actually have in a system. So when you have such huge variations in the gains, what is important is not just the range, but also, for example, a system with a gain of 0.1 and 1 and 10, when I compare them, this system has a gain 10 times more than this. This system has a gain 10 times more than this. Now on a linear scale, if you see, the difference is 1, close to 1. 1 minus 0.1 is 0.9. The difference between these two is 9. It doesn't capture it. It doesn't say that these two are equal. The difference between these two are equal. That doesn't get captured on a linear scale. Okay, so that is when we go for logarithms. Now if I take log of this, say I take log to base 10, I'd get minus 1 here. Log to, with a log 1 is 0. Again, log to base 10 is log 10 to base 10 is 1. Now if you see, these 2 points are equidistant from 1. This is 1 in the linear scale. Now this point, which was 0.1 and 10, they both are equidistant from 1. And that's what actually happens in a system. Okay, that is why we go for logarithmic axis. Now there is a very interesting analogy for this. I had a discussion with one of the physicists I know, and he said that nature actually scales logarithmically. Once we go to high temperature physics, he was working in high temperature or low temperature physics, and he said what you see at high temperatures, when you go for thousands of kelvins, versus what he was observing at very, very low temperatures, he said that nature actually has a tendency to scale logarithmically. So we'll see what it means when I actually apply logarithms, what happens to the function x. So I'll start with the function x. I'm going to take log 10 to base x of that function. I'll start from 0 and then 1 and then we'll go to infinity. This is actually not to scale. On a linear scale, it will look 1 to 0 is a very, very small interval. So this is 0 and this is, I'm going to mark this like this as 1, and this is infinity. It's progressing afterwards. Now, if when I stand on top of 1 and try to approach 0 from this side, and then from here I'll try to approach infinity on this side, it's equally difficult. Okay, it's equally difficult to approach it. Why is that? Say for example, I jump for decades. So first I go from 1 to 10, then I go from 10 to 1000, 10 to 100, then I go from 100 to 1000. I'll try to approach infinity that way. So this is, I'm going from 1 to 10 power 1 to 10 square to 10 cube and so on. I'm trying to approach infinity. Now when I go from 1 to 0, I'll do a similar jump. I'll go from 1 to 10 power minus 1 first, and then 10 power minus 2 first after that, and then 10 power minus 3 after that. Now if you see, it is, I mean, when you actually look into the area, I mean, as you approach 0, it actually looks, it's much difficult to approach 0, because as you are moving away to infinity, you are actually approaching to 0, but you will never be approaching, you know. So that is why when you actually look at this scale, it's very difficult to approach 0. Okay, and I'll take logarithmic function, and I'll now take log of 1 and then show you what happens to this axis from 0 till infinity. Okay, so when I have, I'll just go from 1. So when I take log 2 base 10 of x, what I get is log 1 is 0. Okay, log 10 power minus 1 is going to be minus 1, and 10 power minus 2 is going to be minus 2, and 10 power minus 3 is going to be minus 3, and 10 is going to be 1, 10 square is going to be 2, and 10 cube is going to be 3. Okay, so now if you see, I actually converted them to a set of integers as I'm moving on decades. Okay, it has now been converted to a set of integers. Now they both look equidistant. See, previously on a linear scale, 1 to 0 looks like nothing compared to 1 to infinity. But on a logarithmic scale, the points from 1 to 0, the distance from 1 to 0 is the same as distance from 1 to infinity. Okay, so when you plot the function log x, I'm actually spending a little time on the function logarithm of x, because it's a very important function to understand. We'll be using this extensively throughout engineering, and I find many textbooks don't spend much time on it, so I'll just give some time for it. So if I plot the function log x, the function will actually look something as, you know, log of 0 is minus infinity. It's a very, very small number. You can see that already. Okay, when you go from 10 power minus 2, 10 power minus 3, you get more and more negative numbers. Okay, so when you go to 0, you'll get a very large negative number. And then from 1 to infinity, it eventually diverges to infinity, but very, very slowly. So if you look at this region from 0 to 1, your logarithmic function is behaving like an expander. It is expanding the range from 1 to 0, okay, to minus infinity to 0. On the y-axis, it is minus infinity to 0. And in the region from 1 to infinity, even though the range is very large and the output range is also same, it is actually behaving like a sort of a compressing function. You know, it is actually compressing. It has a very interesting property. Before less than 1, it behaves like an expanding function. After 1, it behaves like a compressing function. So both the points from 1 to infinity and 1 to 0 look the same, or the distances, they look the same, okay, once you apply logarithmic functions. Now there is a very interesting mythological story in the Hindu mythology about this. It turns out the holy trinity of gods, Brahma, Vishnu and Shiva, had a kind of a competition, and the gods Vishnu and Brahma went in search of the Atmaling. So it turns out Brahma went into the infinite cosmos, you know. He actually went to the infinite cosmos in search of it. And Vishnu went into the interstices. I mean, he went into the depth of, you know, the Patal. So there are Sanskrit words to describe that called the Ant and the Adi. You know, Ant is the end and Adi is the beginning of it. So Vishnu went in search of the Adi, that's almost 0. And Brahma went in search of the Ant towards the end, which is infinity. And it seems they never found that. Okay, both of them could never find it. That's a very famous mythological story. It's very much like that. You know, you can connect to this. On one side, you're trying to reach the infinity, and other side to the infinitesimal. Okay, and it's the same. The effort is the same. And logarithmic functions wonderfully capture that. So that is why we go for logarithmic functions. So now I'll just come back to the definition where we actually took a small detour. So I actually said that the gain actually has to be plotted on a logarithmic scale. Okay, so we commonly take 20 log whenever we are plotting gain, which is ratio of voltage to voltage or ampere to ampere, current to current. We just take 20 log of that quantity. In this case it's a transfer function which turns out to be ratio of voltage to voltage or current to current. Okay, so we take logarithm 20 log of the magnitude response and plot it instead of plotting it on a linear scale. Now you should understand that frequency already to begin with varies from 0 to infinity. That there is no doubt. I mean, it is going from 0 to infinity. But the amplitude has a small variation, 1 to 0. But then I told you, as far as amplifiers are concerned, a variation from 0.1 to 0.01 is just as significant as 1 to 0.1. Okay, so which is why we go apply logarithms for the amplitude. And we actually, so now we plot both frequency and amplitude on a log scale. So such a plot is called a Bode plot. Now in a Bode plot, it's easier. I mean, it's as I said, in engineering we try to find easier and easier tools to analyze complex systems. So that's the whole purpose of engineering. So we'll just take. We'll actually go back to the function which we started. H of j omega was a single, or h of omega. Let me write it as. I'll maintain the notational. I'll maintain the same notations throughout. So h of omega, the mod of h of omega is 1 by root of 1 plus omega by omega p the whole square. Now I'm going to take 20 log of this quantity. Now there is a reason why we take 20 and all that, so but that's for some other time. So we'll just analyze this function. Okay. Now to plot this function, what I'll do is first I'll plot it for two conditions: omega much less than omega p and omega much greater than omega p. Now when omega is much less than omega p, this function I can ignore it compared to 1. So it simply reduces to 20 log of 1, which is log to base 10. Actually we should take it to base 10, which is 0 decibels. Now for omega much greater than omega p, this function, this is actually for omega much less than omega p, and for omega much greater than omega p, this function reduces to 20 log of, right, this term is much greater than 1, so therefore I can ignore 1 and write it as omega p by omega, which reduces to 20 log of omega p minus 20 log of omega. Now this is for omega much greater than omega p. We'll try to plot both these functions. First, if you look at this function, when I plot it as a function of frequency, this is actually a, let me just use a dotted line, so let me use a different color. This function is a constant which is at 0 decibels, and this function is a slightly different function. It is actually, when you actually plot, now that I said your x-axis is on a logarithmic axis, we are plotting both on the logarithmic, both on logarithmic axis. So this is also on log omega. If you look at this equation, if you assume log omega as a variable, this is a constant. Okay, this is a linear equation on the logarithmic scale. Okay, so when omega equals omega p, I'll write it as omega p. This function is 0, it matches the 0 dB line. So it will go like this. It will match the 0 dB line and eventually decay down like this. Okay. Now what happens in a Bode plot actually is that when omega equal to 0, it is a 0 dB. When omega is infinity, again it matches this. So the actual Bode plot, when you draw it, it will touch both these lines asymptotically. So meaning it will touch at 0 and it will touch at infinity. It will almost touch these functions asymptotically. At the omega equal to omega p, it reduces by minus 3 dB. I mean 20 log of 1 by root 2 is minus 3 dB. Okay. So that's how you plot it. I mean you just show the minus 3 dB at the pole, then the yellow curve is your Bode plot. Now for phase response, we don't plot it on we don't take logarithm of phase response. The reason is that, for example, let's say we have a phase shift of 0.1 degrees and 0.01 degrees. I'm writing it in degrees. Phase shift can be represented in radians or in degrees. Okay, it really doesn't matter. It's a small phase shift. Okay, but when it's an amplitude variation from 0.1 to 0.01, that's like the gain itself is reducing. The amplitude of the sine wave is reducing by 10 times. That's a big change. Okay, but this phase shift of 0.1 degrees to 0.01 degrees isn't much of a change. So the waveforms are going to look very similar. Or if I go from 0.0001 degrees to 0.00001 degree, it's 10 times less than this. It's really not going to look very different. Okay, but when the gain is different, it's going to look different. So that's why we apply logarithms only for the amplitude plots, and the phase response we still plot it normally, only that the frequency axis is plotted on the logarithmic axis. Now tan inverse function is already a compressive function, so it will go from 0 till pi by 2. I have here I'm plotting it in radians, 0 and at omega equal to omega p. It's not shown to scale, but pi by 4 here. Okay, so let me just pi by 2 once it reaches at this point. Okay. Now, normally for engineering applications, when you are actually showing it as a graph, how do we show it is that we just show it like this. We just show it using straight lines. If you look at the actual Bode plots, as shown as straight lines. If you look at it asymptotically, this is a straight line and this is a straight, and the green line is a straight line. But the actual Bode plot actually has some curvature here. Okay, that when we actually do some hand design of systems, or when we're analyzing systems, we don't show that it's assumed. So we just show it directly like 0 decibels at omega equal to, from omega equal to omega p onwards, it will start rolling down in a single pole system. Now the slope of this line is actually, if you look at it, the equation was 20 log omega p minus 20 log of omega. Okay, since it is logarithmic axis, I'm going to plot it as log omega, but then I'm not going to take log of omega, but omega will be shown on a logarithmic axis. Okay, on a logarithmically we'll be varying omega. It reduces, if I change omega by 10 times, this value will change by 20 dB. So for example, assume omega is, I'll start from omega equal to 1. When omega equal to 1, this is at minus 20, 0, minus 20 log 1 is 0 to base 10 is 0. And when we take omega as 10, okay, this value will actually be, or let me just, because I've used the word omega p, let me use it in terms of omega p. Now if omega equals 10 times omega p, and I'll analyze it, find the value at 100 times omega p. When omega is 10 times omega p, the value of this function is, you will get minus 20, and when omega is 100 omega p, you will get minus 40. So meaning, when I change my frequency by 10 times in one decade, for a decade of change in frequency, the amplitude changes minus 20 decibels, minus 20 to minus 40. So the slope of this line is minus 20 dB per decade. Okay, so that's the way we plot the Bode plot. So here, of course, when you see actually in the reality at omega equal to omega p, you will have a 1 by root 2, there will be a 3 dB bend at omega equal to omega p. But when you are showing it graphically, you can just show them as two straight lines like this. Okay. Now similarly, I can show for a transfer function like this, 1 plus s by omega p. Now the magnitude of this transfer function can be written as root of 1 plus omega by omega p. First I'll substitute s equal to j omega. If I evaluate this at s equal to j omega, I'd get 1 plus j omega upon omega p. Okay. And the magnitude is this, and the phase of this function phi of omega is minus tan inverse of omega upon omega p, and this is your magnitude. Now as you plot the magnitude, again you can see the magnitude goes from 0 to infinity. Again I've told you the motivation for using logarithms. It captures the variations, large variations, very elegantly on a logarithmic scale. That is one of the reasons why we go for logarithms. Okay, so now I'm directly going to take 20 log of this and I'm going to plot this function omega by omega p the whole square. Again, to plot this, what I'll do is I'll just assume two cases when omega much less than omega p and omega much greater than omega p. So when omega is much less than omega p, this term is much less than 1, so it will be very much close to 0 dB. So this is your 0 dB line. Now when omega is much greater than omega p, omega is much greater than omega p, this function can be written as 20. I can ignore 1 and this function becomes 20 log omega minus 20 log omega p. Okay. Now if you see here, this actually increases, this function increases with omega, okay, with a slope of 20 dB per decade. So this function will be at omega equal to omega p, it is at 0 dB. The function would go like this. At omega equal to omega p, it's at 0 dB, and then it increases linearly with a slope of, this is on a log omega axis. Okay, actually omega is on a logarithmic axis with a slope of plus 20 dB per decade. Okay, now the overall response will be asymptotically touching this. At at omega equal to 0, it will be 0 dB exactly, and it will eventually touch this function asymptotically. At omega equal to omega p, this will be plus 3 dB. Okay, so now when I am trying to plot the magnitude response, it will look something like this. If I try to show it using just straight lines, this will start at 0 dB, eventually it will go to infinity, and this happens at omega equal to omega p. In an actual plot, it would actually raise by 3 dB at omega equal to omega p. Okay. Now the phase response, I am not showing it because it's anyways, just for the sake of completion I will show it, but it's a very simple thing. Instead of negative, you are going to get a positive phase response compared to a single pole system. It's tan inverse of omega by omega p. Okay. So this function is going to start from 0 and eventually going to go to pi by 2. At omega equal to omega p, you will get pi by 4, plus pi by 4. Okay, and when omega is infinity, it's going to go to infinity. Again, we don't take this phase response, we don't plot it on a logarithmic scale. Okay, as I said, small variations in phase is not a big concept. It doesn't reflect much on a signal that is being fed to the system. Okay, so we have discussed about poles. Given a pole, how to plot its frequency response using Bode plots, and given a 0, how to plot its frequency response. Now then, we should be able to plot it for any first order system. Okay, so we'll take some examples of first order systems, or we'll take a system like this: 1 plus s by omega z into 1 plus s by omega p. This is a transfer function given to you. Now we have to plot the frequency response. See, I'll just say, once you know the poles and zeros, you can get the transfer function. Once you know the transfer function, then you can get the frequency response. Now your frequency response of this system can be written as root of 1 plus omega by omega z the whole square by 1 plus omega by omega p the whole square. Okay. Now what I can do is, to plot the frequency response for this, I can divide this into a pole and a 0. Omega by omega p the whole square into root of 1 plus omega by omega z the whole square. I can divide this into a pole and a 0. I'm plotting the magnitude here. So we already saw how to plot this. This function was actually starting at 0 decibels, and then eventually at omega equal to omega p, after that it started decaying down or reducing linearly at the rate of minus 20 decibels per decade. Now this function, on the other hand, when I am trying to plot this, it starts from 0 decibels, and then at omega equal to omega z, after that it starts increasing linearly at the slope, with a slope of plus 20 decibels per decade. Okay. Now when I multiply two functions in normal domain, when I multiply it, now I am taking logarithms of it. Once I take logarithms, multiplications become additions. That is one other reason why we go for logarithms, because multiplications become additions, divisions become subtractions. And in most engineering systems, in circuit systems and systems, we encounter cascade of systems. We know we will be cascading systems, so the gains get multiplied. Okay, and going for logarithms, those gains can be simply added now. That's one other main reason for going to for resorting to Bode plots or taking logarithms of the gains. Now, when you add these two plots, there are two cases for this. First, I'll assume a case, there are three cases for this when omega p is greater than omega z. Your pole is greater than omega z, so which means first you encounter 0. So your graph will start at 0 dB. See, first you have to find the gain at DC or gain at omega equal to 0. It is for both the functions become 1. This function becomes 1. This is also 1 at omega equal to 0. So 20 log of 1 is 0 dB. Okay. Now first you encounter, as I said, omega z is smaller. So first you will encounter 0. When you encounter 0, after that your gain is going to increase with the slope of plus 20 decibels per decade. Now after some time you are going to encounter a pole. When you encounter a pole, at that point the pole will try to reduce the line by 20 decibels per decade. So 0 will try to increase it by 20 decibels per decade, pole will try to reduce it by 20 decibels per decade, so the overall gain will remain constant. Okay. Now what is the value of this gain? That you can very easily find by substituting omega equal to omega p in this expression. Okay. Or for frequencies much greater than omega p, this function, for very large frequencies, this function reduces to this function, omega by omega z is much greater than 1, and omega by omega p is also much greater than 1. Both the functions are much greater than 1. So you are going to get omega by omega z by omega p. So this is going to be omega p by omega z. So that's the final value of this function. So this is going to be 20 log of omega p by omega z. We can also see that the asymptotic line here actually is 20 log omega minus this function is actually 20 log of omega minus 20 log of omega z for the 0 curve, and this curve is actually 20 log omega p minus 20 log of omega. So when you add these two functions, this and this gets cancelled, So when you add it to plus 20 log of omega minus 20 log of omega z, when you add these two, you get this. Okay, 20 log omega p by omega z. And to plot the phase response, your phi of omega is simply tan inverse of omega by omega z minus tan inverse of omega by omega p. Okay. So first, when you encounter 0, it increases, it advances the phase. When you encounter pole, it delays the phase, or it actually decreases the phase. Okay. So when you plot it, you start from 0 degrees. First you will encounter this term will dominate because your omega p is much larger, omega p is greater than this, so this term will be very small. This term will dominate, so the phase will increase linearly. After, when you encounter omega equal to omega p, omega z, you will get pi by 4 phase shift, plus pi by 4. Then as the phase shift keeps increasing, when it encounters omega p, the phase shift will start reducing. Okay. Eventually, this will create a maximum phase shift of pi by 2. This will create a maximum shift of minus pi by 2. When the two phases add, you get 0 degrees. Eventually, it goes back to 0 degrees. Okay. So what it means is, now I'll just quickly draw the magnitude response here. So first you start from 0 dB. At the 0, you start increasing at 20 dB per decade. When the pole is encountered, it remains constant. Okay. And the value of this is 20 log of omega p by omega z. Okay. Now, as we try to plot this function, as we try to look at this function, what can we infer is that if I am going to feed a sinusoidal signal of frequency, say cos omega naught t, here omega naught is much greater than omega p and omega z, both included, then you can very easily say that the output of this, the gain at higher frequencies here. So you will be getting a signal with a gain of omega p by omega z. Okay. And an amplitude of you'll have a gain of omega p by omega z into That's your amplitude. If the gain amplitude is 1 here, you're going to get gain here, and the phase shift is 0, because for large frequencies the phase shift is 0 degrees here. Eventually it will come to 0 degrees and go to 0. Okay, so that's the power and advantage of going for Bode analysis. Now before I finish this lecture, I'll just give 3 important functions that you will encounter in first order systems. So one of the common functions you will encounter is the single pole system. It's also called the low pass transfer function. The other transfer function, it's actually s by omega p upon 1 plus s by omega p. Now I didn't show this function, but this is called as a high pass transfer function. Okay, and then we'll have s by omega z, which we just discussed a few moments ago, and s by omega p. Okay, let me just talk a little bit more about this and then come back to these functions. So I just discussed one case when omega p is greater than omega z. So now if you are asked to plot for a condition when omega p is less than omega z, so first you encounter a 0, a pole, and then a 0 later. So first you start from 0 dB. Okay, now as soon as you encounter a pole, your gain would start rolling down with a slope of minus 20 decibels per decade. Then you will encounter 0. After that your gain would remain constant. Now again the peak value of this function is going to be 20 log of omega p by omega z. Now we know since omega p is less than omega z, this number is going to be less than 0 dB. It's going to be a negative number, which means gain is going to be less than 1. In the previous case, when omega p was greater than omega z, the gain was greater than 1. Okay, I'm not showing the phase response, it's pretty simple. The magnitude will have a big change. Okay, now let's say we are asked to plot. Now we'll very quickly try to plot transfer functions for this s by omega p by 1 plus s by omega p. When you're asked to plot a transfer function for this, again you'll have to take the magnitude response, which should be mod of omega by omega p by 1 plus root of omega by omega p the whole square. Now if you look at this function, this is nothing but a 0 at DC. Okay, so your function, I can simply say that when omega equal to omega p, this function hits the 0 dB line. It's just increasing linearly, and when omega equal to omega p, it hits the 0 dB line. And this function, if I'm going to plot it, it's going to be like this. Okay, when omega equal to omega p, again it hits the, if I'm just plotting them on logarithm, I have taken 20 log of both the functions and I'm plotting it. Since I've already spoken about it extensively, I'm drawing it very fast, so I think you already understand that. So now when I'm plotting these two functions, so this is actually the numerator function, and this function, this one is actually the denominator function. This is decreasing at the rate of minus 20 decibels per decade, and this is increasing at the rate of plus 20 decibels per decade. So which means when you encounter the pole or 0 dB line, these two will cancel out and you will get a constant. Okay, so the actual shape of the curve is going to look like this. So it's going to initially follow this. Okay, and after that it's going to, I'm sorry, so this will not increase like this. This is a single pole response. It should actually go like this. This is for the pole alone. I'm plotting 1 by 20 log of 1 by root of omega by 1 plus omega by omega p the whole square. When I'm plotting this function here, it starts at 0 dB and then falls off like this. Now when I'm taking the other function, which is omega by omega p, which will increase linearly like this. Now when you add the two numbers, this is a negative number, so this will dominate. 0 to a negative number will be negative itself. So the overall shape of the function shown in green will follow this function at low frequencies and it will flatten out at higher frequencies. So if I plot this function alone as a function of frequency for different values of omega, you will start at a very low value. At omega equal to omega p, you will actually reach a value of minus, at omega equal to omega p, you will reach a value of minus 3 dB. Okay, and in the steady state, or I've used this word, when omega tends to infinity, okay, this becomes 0 decibels. Because both the slopes cancel out and they'll lead to 0 decibels. You can very easily verify taking 20 log of p, you will get this graph. Now such a filter is called as a high pass filter because it's passing the higher frequencies and rejecting the lower frequencies. Okay, on a linear graph, if I try to plot it on a linear graph, it will look something like this. At omega equal to omega b, you will get 1 by root 2. Okay, and 1 at higher frequencies. On a logarithmic graph, it will look like this. And the phase response for this system, you can easily show it will be pi by 2, because you will get pi by 2 minus tan inverse of omega by omega p. If you take the phase of this complex variable j omega, you actually have a function j omega by omega p by 1 plus j omega by omega p. This is a purely complex number, so the phase shift will be pi by 2, and this function will be minus tan inverse of omega by omega p. So first you should plot this function going from this function. I am plotting the second function going from 0 to pi by 2, and then shift this function by pi by 2. So it will start from pi by 2 and then go to 0 eventually. At omega equal to omega p, you will get plus pi by 4. So it will start from pi by 2, 90 degree phase shift, and eventually go to 0. Okay, so that's the response for a high pass filter. And we will now try to plot the response of an ideal integrator and an ideal differentiator. So which has a transfer function of an ideal integrator, has a transfer function of h is s by omega p, s by omega I, and an ideal differentiator has a transfer function of omega d by s. I made a small mistake here. So the integrator is omega by I by s, and the differentiator is s by omega t. Okay. So now when I am plotting this function, I should take s equal to j omega, and I am taking the 20 log of that. You would get 20 log of omega I minus 20 log of omega. So at omega equal to omega I, so I am going to write omega I here, and I'll call one of the lines a 0 dB line here. So if you look at this line, it starts at when omega is 0, this is minus infinity, minus of minus infinity will be plus infinity. It will start at very high value, and it will touch 0 dB line when omega equals omega I, and then roll off afterwards with a slope of minus 20 decibels per decade, minus 20 dB per decade. Okay. Now I'll actually take a pole, a single pole system with a pole at s by omega I. And if I try to plot the same response on the same graph, the line will start at 0 dB, and then it will coincide with an integrator. Okay. So which means for frequencies much greater than omega I, the frequency response of an integrator is same as the frequency response of a first order low pass filter or a first order system. Okay. If you remember long time back, I said for sudden inputs the first order system behaves like an integrator, and this is the frequency domain interpretation of it. For high frequencies, the frequency response characteristics of both the integrator and the first order system, a simple low pass filter or a single pole system, exactly match. Okay. And if you also see the phase shift, the phase response of this function is simply minus pi by 2, because it's a purely complex number with minus j. And we know for a single pole system, the high frequency phase response is minus pi by 2. So both match. The phase also matches, amplitude also matches. So they both look the same for high frequencies. Okay. And intuitively you can see that here since I'm only plotting it along s equal to j omega, for omega much greater than omega I, this function reduces to omega I by s. I can ignore this term 1, and it will reduce to omega I by s. So that's how for very high frequencies an integrator and a first order system behave identically. Now similarly, I'll now consider this transfer function s by omega d, which is your differentiator. So if you take the magnitude response, you are going to get 20 log of omega d minus so you are going to get 20 log of omega minus 20 log of omega d. Okay. So this function, if I am going to plot it, when omega is 0, it's going to be minus infinity, it's going to start at a negative value, and when omega is omega d, so this is my 0 dB line, when omega is omega d, it's going to when omega is omega d, you are going to get 0 decibels here. Now I'll compare this with the transfer function of s by omega d by 1 plus s by omega d. Okay. Now this transfer function, I'll just replot it. I'll plot it here. So this function, if I'm just I've already plotted this. It starts from a huge negative value, and when omega equal to omega d onwards, it flattens out and eventually reaches 0 decibels. Okay, asymptotically the Bode plot will touch at minus 3 dB, but to show it on a linear graph and using straight lines, it will be just at omega d, I can say approximately to 0 dB. Now, when I try to plot the differentiator here, the differentiator graph, the ideal differentiator will overlap with this and eventually depart after omega greater than omega p. But if you look at this response before omega d, they both look indistinguishable. Okay, so a simple first order high pass filter and an ideal differentiator are indistinguishable for frequencies much less than omega d. Okay, where the differentiating frequency omega d is the point where the differentiator gain is 1, or and if I construct a similar single pole system with a first order high pass filter with a pole at omega d, they both will have similar responses for frequencies much less than omega d. For low frequencies, an ideal differentiator and a first order low pass filter are indistinguishable. They both will have same magnitude and phase responses. Okay, so that's it. These are the points that we will discuss today. In the next lecture, I'll start taking some RC circuits, and then we will do the time domain, the frequency domain, and we'll also find the pole zero analysis, and I'll tell you how to find the transfer functions. Okay, given a function, I'll discuss how to find the transfer functions, and just by looking at it by inspection, we should be able to write the transfer function. I'll stop at this point.